everyone. Welcome to the second seminar of the ICARL Reinforcement Learning series. And today we're honored to have Angeliki Lazaridou as our invited speaker. She's a staff research scientist at DeepMind, and she did her PhD at the University of Trento at grounded language learning. She has done a lot of impressive and amazing work on the field of emergent communication in multi-agent systems, and she's one of the most influential researchers in that area. And I'm not going to stand any longer. So Angeliki, if you want to start, all yours.
Hi, everyone. And well, thanks a lot for having me here. Can the people remotely hear me? Does this work?
Yes, it works.
Okay, great. Good to have some multi-agent cooperation here to make this work. So, okay, today I'll be talking about towards multi-agent emergent, awesome. As a building block of human-centric AI. Well, I guess you can see that actually there. And let's just have this as interactive as possible, just so that, I guess it's interactive. Cool. So first things first, the ability to cooperate through natural language, I think it's fair to say, is a really defining feature of humans. And, you know, it's not just cool that we can communicate with natural language, but it also allows us to excel in very complex problem-solving tasks, like the one you observed just here, you know, 2 minutes ago. But also, you know, beyond that. So language is cool, and we can do amazing things with that because we can, like, you know, talk to each other, negotiate solutions, share experiences, etc., etc. This is what humans can do. Now, on the other hand, we have machines, and we have machines that they have been getting increasingly, you know, more powerful. AlphaGo, you know, we can recognize a bunch of cats on ImageNet and more things. When I started giving the talk, it was GPT-3. In the meantime, it became GPT-3. I think we are very soon to see GPT-4. DeepMind has its own language model as well. So, like, we see a lot of the perceptual and linguistic skills of the deep nets as time goes become more advanced. And so a natural question here arises as whether these models, these machines can now develop a shared language between each other so that they can interact. First of all, so that they can improve their coordinated problem solving. So imagine, for example, what you can do if a powerful language model could coordinate with like a very powerful visual model so that they can, you know, bridge together their skills and solve like a multimodal task. But also so that these models can also cooperate with humans and, for example, aid them in decision making or for any other reason. Actually, we have some evidence already where we know that language communication between humans and machines facilitates cooperation between those agents. For example, because agents can better explain their intentions, their tactics, and so on and so on. So there is something there to be gained by allowing those machines to establish some common ground with themselves and with the humans. I'm pointing.
Yeah.
There. Cool. Okay. Now I'm going to breeze through a number of like not related, but like a number of things in multi-agent communication. But basically, what I want to first say is that multi-agent communication is not a new thing that started in 2016. Multi-agent communication has been there in the literature, for example, in 2010, even Ellman has done something of this sort at some point. But what happened in 2016 was that we started seeing multi-agent communication being attacked with deep learning. So it's the same basically deep learning revolution that happened everywhere. Also came to multi-agent communication. So we started seeing emergent communication work, first of all, with deep reinforcement learning. Then we moved on from making the visual input of agents slightly less trivial. So for example, from raw pixel data, we started seeing emergent communication not anymore in cooperative agents, but in agents that exist in complex competitive environments, for example, like StarCraft. We started seeing emergent communication in environments where agents are not just exist in 2D, but they're fully embodied in 3D environments where everything just, it's not just a third dimension, like everything becomes more complicated. We started seeing work as well in interesting environments where agents are not competitive, are not cooperative, but like self-interested agents. So there needs to be some notion of negotiation and convergence to mutually accepted general sum, basically, situations rather than zero sum. And finally, we started seeing work that tries to close the gap between what I was talking now and what I was saying in the beginning. So allowing these agents now not just to emerge any kind of protocol, but that protocol now being grounded in natural language itself. So this is like a brief overview, and if you're interested to hear more, together with Marco Baroni, who was my PhD supervisor in Trento, we wrote a literature review that we discuss some of the things that I'm also going to talk about here today. So anyway, after this like long and painful introduction, the main thing that I want to answer to discuss today with all of you is whether multi-agent communication can actually be a building block of human-centric AI. I'm going to start by concluding that, it can, like it very much can. I think we can, we can do that. But before we do that, there are like a couple of boxes that we still need to tick. So we are on the right path, but we can get faster there if we do a couple of things more. And so today, I want to spend the remaining 45 minutes exact to talk a bit what I call the headaches that we are currently facing in the field and have basically a discussion with all of you here about those points. Also, if you have like similar experience, I would be interested to know, because these things are not necessarily about multi-agent communication per se, but it's more about general notions of learning and deep learning as well, and reinforcement learning. So it's the whole combo. And before we get to the headaches, I'll set up a common ground with people here. Are you following multi-agent communication literature at all? Not at all? But you know the term, right? Cool, okay. That's good. Okay, so we'll establish though. So the common ground. Like I'll go through with you a typical communication task. Do we have questions? Okay. We'll then talk about what is the typical experimental setup that people in emergent communication are following, and then having established that, I'll go on and sort of complain about the things. Complain through my own work as well about the things that I think we can do better. And finally, point to some mitigation of the headaches. Okay, so a typical communication coordination task goes in the following way. In the vast majority of the cases, at least up to recently, when we talk about multi-agent communication, most of the times, a lot of this research happens in the context of like a referential game. Do people know what a referential game is? No, fine. It's very easy. So in the referential game, we have two agents. We have the speaker and the listener. And we have two images. The target image, which is the one on, well, it says target, and the distractor image, which is the one that is not the target. Okay, that becomes very complex all of a sudden. Okay, I'll just give the gist. And the target, the process is the following. the speaker knows the target, the listener doesn't know the target. Now the speaker needs to tell to the listener which one is the target. And it will do that by using some sort of communication. So it will communicate to the listener. Now the listener will take the communication, and by looking at the target and the distractor, the listener will use the communication to pick which one of those two is the target. Now, you can see why this is called a coordination game, right? Because both of these people need to coordinate to the right answer, which is the target. And you can also understand why it's called emergent communication, because the speaker, well, actually you cannot see, I'm going to tell you now. So because the speaker and the listener, they start from, tabula rasa models. It can be neural nets, for example, so random weights. And through this process, they learn basically to coordinate. And because we don't teach them how to coordinate, this is why we call it emergent communication. So this is what they explained, but more in the more as an RL task. So we have the speaker, we have the listener. Both of these are learners. The action of the speaker is some symbol, some sequence of symbols. This goes to the listener, and then the listener, by using the symbols and observing the state, which is the distractor and the target, is making their own action, which is left and right. And then this is then used to decide the reward. And so this is basically, it's a very simple reinforcement learning setup. Is this more or less clear? Okay. And that's it, basically emergent communication. I think that's, and I mean, then that can get, arbitrary, more complicated, and like it can be multi-step, it can be, not from pixels, it can also have more complicated actions, but if you know this, you know everything. And usually, I mean, also the type of learning, like it can be Q learning, it can be this learning, but because in this simple setup, it almost takes the form of contextual bounded, even things like, reinforce, which is like the simplest, like type of update rule could work in these setups. Okay, cool. So that is the communication game. Now, the typical experimental setup goes in the following way. There are n fixed agents that communicate. In most of the cases, when we talk about multi-agent communication, we see 5, like we see something less than 5, but really it's 2. Like most of the papers, they have 2 fixed agents. Maybe that has been updated to 3, but it's closer to 2. And okay, so n fixed agents, cool, we take a note of that. The next step in this experimental setup is that we generate a set of initial states using, one environment and some specific rules. So we pick that, for example, referential game with images that usually come, from one data set, that, for example, being ImageNet, and then we pick distractors and targets in some, particular way. So usually we have, one target image and K distractor images, where K is most of the times, if not always, fixed, like 5 distractors or 6 distractors, but it's the same throughout the whole game. Okay, after we do that, then we split the initial states into train and test. Not always. I mean, this is RL, and we don't necessarily split our train and test, right? We evaluate on our training set, which is sad, but it's true. However, there is like a lot of work actually that does a lot of nicely experimental setup, and we see, very careful splits of train and test that, really tries to answer how these agents generalize to various splits. Now we take these n agents and we train them together until convergence. And if you have a lot of CPUs and GPUs, that means basically, almost forever, like, I don't know, n,000 steps. 2 agents together, right? These 2 agents, to maximize task success. And then for final performance, first of all, we almost always look into the same agents that were trained together until forever. So we train them, these agents, forever. and then we see how well they can coordinate together. We somewhat often report performance of only one training run. This sounds familiar, I think, especially in deep RL. Like, this was an excellent talk by Joel, 2018. I think this still hurts until today. Yeah. And finally, we very often in the multi-agent communication, we like to talk about properties of protocols, but we only talk about properties of protocols of one particular run. Which run? I don't know, SIT 42. Okay, so this is the experimental setup. Does anybody notice anything weird already? Very nice. So these are two examples. I have three more headaches. So basically, the point that I'm trying to make here, and your colleague also spotted, this is like a good experimental setup, but we can do better than that. So we can start improving things. We have started seeing improvements already, but we can do better. And now I just want to talk a bit about these headaches and just to try to make some points. First of all, we use a specific environment and we train agents, and then we look at properties. Unfortunately, the environment design that we are going to choose for our agents is going to determine the properties of the protocols that these agents are going to learn. In plain English, and this is my own work, by the way, so I'm just complaining about my own work here, if that wasn't clear. So we took the experiment, we took the referential game, and we made small changes in the environment, like really small changes, like from 2 destructors to 20, whether the object set was balanced and whether, you know, the viewpoint of the object was the same or different. So in the grand scheme of things, this is not like big changes, just small changes. Okay, so these changes actually led to quantitatively similar task success. And task success here is just accuracy. Did the listener find the right picture as the speaker? So you see train and test, there are changes, yeah, but I mean, like, it's not like, you know, 70% and 100%. It's everything fluctuates, let's say around, I don't know, like 90%. However, when we look at how the protocol looks like, we see that in the game A, the agents came up with a lexicon size of 1,000 unique symbols to communicate about all the data set. But in the game D, the agents developed only a lexicon of 5. So day and night, really. Like, it couldn't be more different here. And not only the protocols look different, like if you look at them, the properties of the protocols are also inherently different. So topographic similarity is one of these measures that people like to use in the multi-agent communication to talk about how compositional the language is. So you can think of it as a proxy of compositionality. It's not perfect, but it does the job, basically. And you can see that the topographic similarity of game A is 0. It's a correlation. So it's like 0.13 is, you know, there is some pattern, basically. But in the game D, the correlation drops on the floor. So basically, yeah, small changes in the environment, big changes in the protocols. Like, another perspective of that is that because of the fact that in one environment we can see one protocol, and in the other environment we can see another protocol, there has been work where basically has says that have found basically that emergent languages exhibit, sometimes often counterintuitive properties. And in this particular study, the authors found that in the emergent communication setup, the zips flow of abbreviation. So the fact that frequent words, tend to be small, shorter. For example, take the word the, that is like tiny and occurs like every third word, versus some like extremely, you know, specific term like backpropagation, which is not very often in the general lexicon. Okay, this is what happens in natural languages. And this has been optimized, you know, one of the theories like for effective communication. But in emergent communication, we've actually seen the exact opposite. So agents actually exhibit the opposite behavior, where frequent words tended to be longer, right? So why does this happen? Well, this actually happens because the listener has more chances of guessing correctly the longer the message is. So the speaker, because the listener is going to guess correctly something the longer the sequence is, then this means that the speaker is going, without any inductive bias, is going to, you know, it will do best response to that behavior of the listener. So it would generate longer messages. Of course, if we would, yeah. So it can be, I mean, it's usually done in different ways, but unless, like usually in most of the cases, the speaker sends like the whole sequence. So I'm going to send you like, you know, 10 things at a time. And then, but the length is usually optimized during the game. So it can be variable length. The point here is that if we, like, depending on how the environment is and depending on how we organize the environment, like if we had here some laws where it would say, try to send, for example, the shorter message possible, this won't really come up on its own unless we put the bias there in some way. Yeah, so basically all this, like this, the way that we set up the game is going to affect whether agents are going to emerge that property or an under property. This conclusion, you know, might have been different in a slightly, you know, altered game. Now, that was typical headache number one. Typical headache number two is that task success is guaranteed. That's like the great thing with emergent communication. No matter what you do, you're going to get 90% performance. Well, not exactly, but I mean, you know, backpropagation works, but sometimes, you know, optimization is difficult. But the bottom line is that it's crucial in emergent communication to not just rely on the task success. Did my agents achieve in solving the task? But dig into, like, you know, how are the agents solving the task? Like, what are they really communicating about? And we have seen a lot of work, a lot of good work here, trying to measure this in similar ways. So either moving away from the like from the IID trained split to, like, you know, to really try to test if agents are learning, you know, some sort of like composite meanings. Compositionality is one of the, like, let's say, crucial properties of emergent of natural language. And it's also important to be checking our protocols for that. And they have been currently, you know, two measures in the literature that test for that. One is the TRE metric, which essentially tries to see if the message decomposes in all the right ways with respect to the language. To the language message that would, well, to the language semantics of the natural, of the intent. I'm not sure if that makes sense, but so you see an image, for example, you made the communication, you try to see if the message is covering sort of all the intent of the object you're communicating about. And the topographic similarity, which as I briefly mentioned before, is trying to capture if there is a systematic relation between form and meaning, between what the agents communicate and what is the object that they need to communicate about. So yeah, measuring properties is super important. It's not always done, but it should be done. Next, learning with static pairs of agents. So again, in my own work, we found that agents were able to play the referential game of 500 concepts with almost perfect accuracy, using only two symbols, A or B. Magic. I mean, this is deep RL, right? So 500 concepts, not 500 images, by the way. There were more images per concept, but like there were 500 concepts, like dogs, cats, and 498 things. So this was like a quite surprising result to us, because we're like, oh, wow, I mean, two concepts, what might those be? Oh, if we look into cognitive science, you know, we know that the most basic splitting of objects out there is whether something is animate or inanimate. So like, yeah, I mean, you see what animate or inanimate is. Was that happening? Not really. Because the very same agents can still achieve almost perfect performance when at test time they were given, you know, completely random, you know, Gaussian noise. So were these agents communicating about cats and dogs? Probably not. I mean, I don't think I can see a cat or a dog. I mean, I know that like the quality is not great, but trust me, there's no cat or dog in the picture. So what's going on here? Well, what's going on is that, I mean, the agents at the end of the day, you know, they're becoming very clever. They have a task to solve it, which is to communicate about what they see. And they try to put the minimum effort to achieve the maximum performance. So the agents really learned the optimal protocol under the particular situations. And the optimal protocol in this way, I mean, for us, I guess humans, it was going to be something like, you know, cats and dogs, because this is what is optimal for us. But for agents that have no bias about how to see the world, when we tell them, you know, do whatever you can just to tell apart those things, they're not talking about cognitive categories. They talk about, in that particular case, about pixels. And a very simple rule that can be inferred from this game when you just see pixels is whether pixel 32 has higher or lower intensity for the target. And that is a perfect almost strategy to solve this particular game. Like, you don't need to do anything more clever than that. Now, is this a problem with our agents? Should we go back and, I don't know, take our agents and not give them food for 10 days? No, I mean, this is not the problem of deep learning. Like, it's not the problem of like our nonlinearities. Why? Because humans exhibit similar behaviors. There is a very nice study by Brennan and Clark where they found that if you take two people and you let them communicate for a very particular reason, if their only goal that these people have to do is to communicate and they stay together for a long time, they're going to develop conceptual pacts, so conventions basically between themselves that are not understandable to other people. So when you basically have a stable partner during training, and then, you know, you also like train until convergence for like many zeros of iterations, you are in this setup where you are, one is basically pushing their learning agents not to learn about communication in general, but to learn about co-adaptation. So this is all basically comes down to how well these agents have co-adapted to each other. And just to give an example of what a conceptual pact is, you have a friend and, you know, you might have your inside jokes, right? And like, unless you've heard this inside joke, like it's impossible for anyone else to know what's going on. So this is something very natural. And it's coming out because of static pairs of agents. Now it's interesting to think like to what degree, you know, we see this happening in machine learning, because it's the same thing. Like if we have a single only data set and we just train on this particular data set, are we solving a task or are we solving a data set? I mean, it's the same problem all over the place, basically. It's just here instantiates in this like extreme, the decision boundary is like a bit too extreme. Now, task success is not a signal of whether communication was successful. So, which is somewhat unsurprising, but this is like a very particular case that happens, especially when agents are grounded in environment. So like when agents basically can communicate not just with their words, but with their actions as well. So yeah, so basically if we solve the game, and I don't know if that's clear, but like if, let's say that in this metaverse, we are all agents, right? And we move around. And let's say I manage, like we need to coordinate, and like, we see task success, like we coordinated. Was it because we used linguistic communication or because we communicated in a different way? So if you can see me, I can convey so much to you, just, in a non-linguistic way, in an extra-linguistic way, by my movements, by my body posture, etc., etc. So again, in these fully embodied environments that I showed in the beginning, it's trivial to just use task success as compass of communication. So again, it means that we need to move away just from anecdotal qualitative evaluations, just look at the communication and see, yeah, that seems like a good communication. And just try to force ourselves to do more causal evaluations of communication. And this causal evaluation of communication was also, for example, what drove our work with Natasha, where we wanted basically to learn communication such that this communication is useful for the other partner. So there is something basically to be gained from the other partner by following our communication act. Finally, so we started this whole rant or like path, on the headaches from the very beginning, which is like, we want to arrive at a place where we as humans can communicate with our machines in natural language, because that's what we are good at. However, if we just narrowly focus only on emergent communication, this on its own does not guarantee that the same agents that can communicate with another agent after a gazillion iterations until convergence will be able to communicate with humans. Yes, and one of the reasons here is that we make this assumption of like stable partners. So we need to close the loop in some way. This is not just about, because somebody would say, yeah, fine. Like you didn't use language. So how do you expect, if you haven't used language, to communicating with the humans? But this is not just about language. It goes beyond that. It's about this very simple pitfall of co-adaptation, that you have two agents being in the same environment and adapting to whatever weird the other agent is doing. So there was this excellent paper at NeurIPS where they found that humans cooperating with machines that were trained via agent-agent interaction, so self-play, there was basically not that much transfer happening when going from agent to human. Because in this cooperative game, the agent, the Overcooked game, right? Where things run around to like cook the food, right? So basically what the authors found is that when they were training agents together, the agents have developed some like weird conventions. You remember conceptual pacts? Right, but on the grounded space, like with actions. Because you remember, agents can communicate also without talking, just by acting. And so like when they trained in this way, then when they took the one agent out and put the human in, the human was like not aware of like the weird convention that the agent has picked up. So this is beyond just language. Of course, this trivially, transfers to language as well. And what we found there is that there was like little to no relation between performance in self-play to communicating with humans. And yeah, so basically what this means is that if you want to close the loop, we need to start putting natural language into this emergent communication. So have it being less of an emergent and more of a multi-agent communication. And so like when we talk about multi-agent communication with natural language, what we mean is that, the agents are able to achieve the game. So it's the same business that, the speaker should say something and the listener should find it. But now this action should be natural language and not just look like natural language that, oh, I've seen this word, I know this word, but rather that, oh, I know this word and I can actually, immediately understand what the speaker meant. So one way to do that, which is what we did in our study, and by the way, this is not an easy task. Like you might think, oh, okay, that's easy. We are just going to put some natural language here. Like what stays? I mean, should be easy, right? So we did it's easy, right? So we put a pre-trained language model. It was not a GPT-3, but I'm pretty sure the same results will hold even if it was GPT-3 or Go for whatever your fancy language model is. So we gave it to the speaker, and then we optimized the whole process with reinforce, with the same business. And we didn't do that only one way. We did it in like a battery of ways. So like we tried to give language to agents and have the speakers use the language model in all sorts of ways. We did yes. They're just stupid answers. That's
how you show that it's binding.
Exactly. So there are, that's why I said it's not like an easy way to do that. I mean, and there are like ways and ways that this can be done. If you just give a language model and you don't make sure that there is some link to the image, it's going to be very difficult to make it work. Now, it's also going to be difficult to make it work if you assume there is a link, because the moment that the reward goes to the language model, like it's just like a very brittle optimization happening. Just to explain why that's the case, like in any grounded space, I mean, if you optimize with rewards, what's the worst thing that can happen? The agent can do an action twice, right? Left, left. Does this matter? Not so much. I mean, who cares? Like if an agent does left twice. Now, if in language, I say a word twice, that's not a good example actually, because pragmatically it might have a meaning. So that's a better one. So if I start doing weird things like that break away from syntax, for example, it's going to be very weird to people. So yeah, basically it's not easy. Even if we try to establish a link between the language model and the images. In our case, for example, we used a pre-trained captioning model. So there was already some link, but even in that case, it was extremely, extremely difficult. So we did like all sorts of ways to try to have a speaker use the pre-trained language model. So in our case, basically, the speaker had a captioning model that would caption an image in a particular way, but that captioning model needed to be adapted through reward learning so that the captioning is now essentially contextual to the distractor. Because, because for example, it's clear why, right? So like if you have an image and the caption says there is a cat on the image, if the distractor is also a cat, you cannot just say there is a cat in the image. You'll have to say something else. And that something else, we were learning it with rewards. Like we didn't have supervised data for that. Okay, I think I explained it today, but you get the point. So forget about the easy split. The easy split is it's an easy split, essentially. We will just look at the difficult split because we are advanced. So the joint performance is the co-adaptation. So how well the two agents do together. Functional only is emergent communication. Structured only is supervised learning, so using captions. Structural and functional is the combo together in different ways, like multitask, re-ranking, noisy channel, like fine-tuning, blah, blah. And the bottom is a ground truth. We don't care so much about it. We are not that good. So the joint is the co-adaptation. The human is when we take out the listener, we put a human listener. So what we see here is that if we only do self-play, these agents are great. They solve the task, they have a language model, they do it with images. Awesome, 98%. You put a human in 50%. 50% is random baseline, by the way. So case in point, right? Just doing optimizing for emergent communication, it's without any bells and whistles, is not going to give you anything. You need to put language in some way. So what we found here is that by combining reinforcement learning with language models, we were able basically to go from 50% to something higher, right, to 70% and 86%, which in different ways. But most importantly, if we use as validation how well the self-play is doing, like one is pointing to the left and the other is pointing to the right, right? Because the joint, so the co-adaptation is at 94%, but the human is at 71. And the noisy channel, which is better for the human, is somewhat worse for the self-play. So if we were to just, forget about humans and say that, oh, we'll just, pick the best model and that will happen. Even if you put natural language in the middle, this is not enough, because here we will just pick the wrong model, basically, if we're doing cross-validation. So how do we use the reward with a language model? We can do several things. We can do reward fine-tuning or multitask learning. If you squint, these things are the same. Like where they differ is the scheduling of the updates. But basically, you assume that for every image, you have a caption. And then you do a bit of reinforce. And then, for example, you do a bit of captioning. That's like a simple way. But I mean, you see what happens there. You have two gradients coming at the same time. It's like a very messy thing because of the problem that I explained before of the twice, or meaning. Also, like it's also, not extremely trivial, especially because, for example, we can have a captioning model that only takes one image as input usually, right? But now the speaker has two images. So even in this particular case, it means that we need to do something else to that language model. Like we need to introduce conditioning from one image to two images if we wanted to do the fine-tuning case. Like even all these things are fine and we are fine with that. All this business results in us, pushing gradients at the language model. So if this was a GPT-2, we would need to touch, 1.5 billion parameters. GPT-3 has, I don't know, 76 billion parameters. Gopher has 508 billion parameters, like a lot of parameters. So like there needs to be something better out there. The worst thing is that even if you can do all these things, is that if we are not careful, which most of the time we are not careful in our life overall, that's just a rule. This causes catastrophic forgetting of the language skills, leading to issues with fluency, which is the twice that I called before. So in our case, we wanted to just not deal with all these problems that I described here. And instead, what we said is that we are going to take another look at the problem. And instead of, using the language model and the reward to back propagate over it, instead we're just going to do something, easier. We are going to use our captioning model as a proposal model. And then we are going to use the reward that we get as a way to learn to re-rank. So we are going to sample many things. So not just there is a cat, but there is a cat, and if you increase the temperature, then you'll get variations of there is a cat. And then the reward will be helping us to trim that down to pick the right candidate that satisfies both that being language and also the listener, doing the task with the right sort of caption. And we also had this theory that, this is a nice thing, we do it with base factorization, and we factorize the problem into, what to communicate and how to communicate. And now the reward does not touch the language model anymore, that we are solving the problem, because the reward is just touching the how to communicate, which is the re-ranking, the what to communicate, which is the re-ranking bit. The final thing I want to touch on is the fact that when we put language models and rewards, we have a drift. This is called language drift. And this language drift is actually multidimensional, and it takes like different flavors. So the first type of drift that usually exists is, when the message is not fluent, we send rewards back to our language model. And if we are not careful, we see things like it is on the fire. Basically, our language models is on, like there is catastrophic forgetting, and the language model starts losing its fluency. The second thing that can happen, and we saw happening, is that there is semantic drift. So the message on its own might be accurate, like it might be proper grammar, but it's not talking anymore about what we see. So instead of, it starts losing that link, as you were saying before, between the actual word and the semantics. And we had things like it is raining on the car. There's no car, it's a fire, clearly. However, the final drift, which was it's like the most difficult drift to deal with, because it doesn't have to do anymore with syntax and semantics. It has to do with pragmatics. It's basically when the message is right, it really talks about what there is in the image, but it leads to the wrong interpretation by a human in the context of the task. So what we saw sometimes was that the speaker would say, Jenny's sitting, and the listener, like magically, miraculously knew what the speaker meant. Like, as a human, Jenny is sitting, it's not easy to understand which Jenny is sitting, because both Jenny is the person on the pink. But what had happened is that because our agents had co-adapted, Jenny sitting didn't just mean Jenny sitting, it meant Jenny sitting and pixels at the top are white. So this can happen, right? I mean, it's up to them what attention they wish to ascribe to the semantics. So yeah, these bad things can happen, and if you do this, have this in mind, and there are also measures to detect. I would say that the pragmatic drift is the most difficult one, because it assumes access to how a human would interpret it. So yeah, like finally, this is like a more recent work that tries, to get away like a lot of these headaches, and I'm really happy actually about this work. So the bit that I'm really happy is not because we used population, so not just two agents, right? We used populations, not static. We used dynamic population, so they're all the right keywords on the title. But we didn't just stay on the task success, right? We did a battery of evaluations. So we evaluated the language evaluation against data sets. So we did Blaise score, for example, against some data set. Of course, this is not great, because like when you do RL, ideally you want to diverge a bit from the actual data set, because you want to make it basically contextual. But it's one evaluation. We did evaluation with unseen agent partners using natural language. Again, which was not perfect, but it was, you can see communication happening. And it also had communication with humans. So multidimensional evaluation that can really tell us not just whether agents are co-adapting, but whether agents are really communicating. So co-adaptation is not about, so communication better is not about just co-adaptation. There needs to be some generalization in there. And this is, I guess, in general about, machine learning. Okay, final words. Yeah, we managed as a community to come, pretty far and tackle important problems with respect to representation learning from raw data pixels, sparse rewards, non-stationary environments, like a lot of advances everywhere. And we can, as I said, I started this talk by concluding that, yeah, we can do there. And we can, accelerate that doing it by basically, tackling some of the headache points. And, in the meantime, like a lot of these things are being tackled as we thought, but, we can do better by making our simulations more realistic. So this is another work that we did with Rama, where Rama did it, I didn't, but I'm on the paper, where basically takes emergent communication and just scales it up, like in all sorts of ways, populations, data sets, type of learning. And it's interesting to see what happens when you go away from the toy setups to like the realistic setups, because many of the things that we thought were fine are not fine anymore. And finally, like testing communication abilities and not just memorization abilities. Like we can do better than that. So evaluate the ability of agents to really communicate with new agents and also communicate with humans. And that's it.
Okay, so if you have any questions from us, means questions, also the people online, if you have any questions, please feel free to unmute and ask.
I have a question. In headache number 3, where agents were able to use 2 symbols to communicate between 500 concepts, how many distractors were used in that setup?
True. I mean, one distractor and one.
Is it possible that they're just saying it's choice 1 or choice 2?
What is 1 and what is 2?
So like A would be the first.
We were switching. I mean, it was like we were randomly switching what is left and right for the speaker and the listener. So, like you.
The
With 50% probability, we would change the order of the pictures from speaker to listener. So even if you
what they see is different from the.
Not constantly, it's like, but 50% of the time. So
Yeah, I see.
like 50% of the time. So this is not basically a solution, but it was like our first guess as well.
I was wondering, when you were mentioning that they try to give as long messages as possible to give as much bias as possible, you mentioned that you ground in the environment try to avoid that to happen. And I was thinking, what is typically done? I mean, the first thing that occurred to me is that giving penalization rewards.
Yeah, that works. I mean, no, this should work, right? Because if you put it in the loss function, like backpropagation will do its work as a regularization. So this works, but if you don't put it there, then should the environment had been different, like that, like could have gone either way, basically. Like, I'm not sure if it makes sense, but in that particular environment, you need to put a penalty. But if the environment was a bit different, like for example, very small difference, like you have a random cutoff, right? You just randomly cut the message at, randomly, like you don't send the whole thing. That would also make agents to have shorter. Yeah.
And you were mentioning as well that having a different number of agents changes that. Have you evaluated if having to communicate to more agents makes them not to send so many biases in their messages, like with the dynamic population that you mentioned?
Yeah. So interestingly, having static like if you have many agents, if this is static, like if I always have the same 100 agents, like adaptation is delayed, but it will happen. Don't worry, it will happen. It will happen. So yeah, so like basically just not having 2 but having 100 on its own is not a solution, and it's expected, right? Because like the learning dynamics, the learning dynamics are nonlinear and we never know what happens with certainty, but this is empirically, this is what we saw, and this is actually of course, like if we go to this is what it happens. I mean, if people sometimes find the opposite result, but this is primarily because, when you train 2 versus 100 agents, usually the baselines are not the right ones. So anyway, basically you need more things than just like increasing the number of agents, doing some more, like taking care of the population in a slightly different way, like squeezing more out of the population. And this is actually something that Rama, on the last paper that I pointed, the emergent communication at scale, was looking at.
What are the best steps for avoiding these messages? Is it along these lines, or something else?
Yeah. So having the human in the loop, basically, it's so interestingly the re-ranking method that we had drift, but it didn't have like as much drift as the other method. So it's not that drift, it's a binary thing, it's there, it's not there. You mitigate the drift, and we were able to mitigate it to some degree by, constraining so that the action space is not just words, but, complete utterances. But other than that, having the human in the loop is probably like the way to go.
And do you think it would be possible to train an agent with imitation learning or something to kind of really copy human-like behavior, so that you don't need an actual human in the loop, like in human-like agent in the loop?
So this is one of, so we actually have one experiment here, which I'm not showing, where basically we distill a data set into the listener, and now we play against this listener, which is distilled. So it's not quite the human, but it is proxy to a human, and that actually does improve things from doing complete self-play, and it's not actually the human. So yeah, that's also like one way to mitigate that. And then other ways, like having, many of these, like not just one fixed listener where you distill the data set, but, maybe having 5 of these, because like what are the chances that all 5 will be pointing to the same wrong direction? Yeah, that's it.
Okay, so we are out of time. Thank you all for coming. The next session will be on the 21st of April with Hatman Amar from UCL Huawei coming again with us about reinforcement learning. Hope to see you there. Thank you for coming. Thank you all.